Throughout the course of history, there have been periods when mankind made rapid advances. And then there are those other, much more numerous times that remain rather unnoticed as transitory periods. Now, at the dawn of the third millennium, how will this age be judged by posterity? And more importantly, what form will that posterity take? And what kind of judgment will it be capable of? For soon, much sooner than we anticipate, mankind as we currently know it might radically change.
Burn, baby, burn!
Something new is emerging. While people have talked about global peace, the end of history, and the disappearance of ideologies, an army of scientists around the world has continued working in their laboratories. The impact of this work is now slowly surfacing. Technology is about to take over the torch of history and will guide us to a new era. The disparate activities of scientists in the fields of genetics, robotics, artificial intelligence, bionics, and nanotechnology seem to be converging towards one goal: to transcend human limits. It will lead us inexorably towards a transhuman age, an age when more evolved species will leave mankind behind as a fossil in history.
We are shifting to a transhuman base. We've come out of a humanist time, and now we're redefining what it is to be human.
Whether we like it or not, we're becoming cyborgs. We're becoming transhumans.
We have the opportunity now to try to do things better than nature has done.
Why not have a stronger arm than we have? Why not be able to run faster? Why not be able to have tougher skins?
If you're going to replace your eye for vision, why limit it to visual? Why not give it the kind of vision a bat has? Give it ultrasound.
Could you imagine a Versace body design? Can you imagine a Terry Mugler body design? These individuals, the late Versace was an incredible designer. What if he was a transhuman? What if he was an artist who really wanted to combine art and science? I bet his designs for a future body would be astounding.
We really, really do want to violate human limits now, and we're getting closer and closer to the ability to do it. It's what we want.
And here we are in the brain research laboratory. Yeah, here's the brain when it was stored.
Dr. Robert White is a neurosurgeon at the Cleveland Medical Hospital in Ohio.
Now here are some pictures.
In 1963, he performed the first experiment to keep a brain alive outside the body.
This is a human skull here. That's not real. This is a gorilla. See here, when you take the brain out and isolate it, you can take all that if you want, and you keep it alive and live forever. See, this is a human brain actually, and it is fixed, so no one needs to worry about it being alive. There have been many attempts throughout the world, particularly in the old Soviet Union, to take the brain out of an animal, they like the dog, for example, and keep it alive with machinery. Now you can do that with the heart, the kidney, the liver, the lung, all the other body organs, solid organs. But nobody had ever been able to do it with the brain. And part of the reason is we must remember the brain is very delicate when it comes to its blood supply. And so when we finally did it and found that this brain of a highly developed animal had brain waves, had biochemistry, was functioning just as it would. Now we couldn't talk to it, we could send it electrical signals, we could show that it could actually hear and so forth, but we didn't know whether it was processing the information. But the point of it all is that that moment in time also said to us, if you can do it for the animal brain, you could do it for the human brain. This incredibly brilliant scientist, Stephen Hawking, who's an astrophysicist actually, he is now in a wheelchair and literally speaks via a computer. And some people, perhaps unkindly, have described this wonderful man as sort of a head on a computer, basically. But he would be somebody who potentially could survive his diseased body through a total body transplant.
To prove that the brain was in fact functioning normally while in this state, Dr. White needed to undertake a second experiment, during which he succeeded in transplanting the head of a monkey onto the body of another. The creature survived for 7 days before the body rejected the head.
In the monkey experiments, these animals are as much a monkey as they were when they were in their own original body. So I would presume, and I'd go beyond that, I would be assured that the monkey personality is retained. So consciousness can be transplanted. Obviously, personality, if you want to speak of the monkey having personality, can be transferred. And so you might ask, where did this bring us as far as the human spirit or soul goes? And I guess you could argue it can be transplanted.
We are now becoming the objects of conscious design. And the implications of that are just enormous, because until now, we've been reshaping the world around us. And we can see how dramatically it's been changing. I mean, we've really reshaped the landscape, and we've built a society and altered society and changed everything that's external to us. But somehow we imagined that we were going to remain the same, that we ourselves were not going to be caught up in this process. And that's not, in fact, true. We are going to remake ourselves. And it's very difficult to deal with, because it will rip free all of the anchors that have until now told us who we are as human beings.
We're at the end of a definition of what a normal human being is.
Every living thing is defined by its DNA code. The DNA is a long string consisting of 4 different molecules called A, T, C, and G, found in all living cells. So it is, in essence, a digital barcode that defines us as humans, just as it defines every other life form on this planet. Only the variety of combinations of these 4 elements makes us differ from one another. The Human Genome Project was started in 1990 as the largest technological enterprise ever, with a budget far outstripping that of the race to the moon, and involving hundreds of laboratories around the world, all with one main goal.
Fundamentally, it was about determining the complete sequence of the human genome, the 3 billion letters that make up our genetic blueprint. And we know we have the code before us, and it's truly remarkable. It is a digital code, and buried within that code is information about what are all the genes necessary for making a human brain, all the genes necessary for making a human liver or the heart or any part of the human body. And now the fun stuff begins, because we get to start to crack that code, having the order of the letters in front of us. But fundamentally, it is very much a digital code.
The secret of life itself, the DNA molecule, a genetic discovery that could give man the ability to create life to specifications. With it comes the power to change evolution itself. Never have we had such opportunity or such awesome responsibility.
Change DNA structure in the lab is fairly straightforward and it's fairly simple. You can study a piece of DNA to unravel its function. You modify the composition and you see what the effect is on function. That's daily routine in a lab that has this technology. Going from the lab to the person to therapy, in theory, is the same thing and is as simple. In practice, it has been shown that it's a lot more difficult. And the reason why it's so difficult is not that we don't know what pieces of DNA to put in, is that we do not succeed sufficiently and at a high rate in getting these pieces of DNA in the right cells. But we have learned how to do it from nature. What is a viral infection? It's a virus that sticks to the cells, that enters the cells, and that uses the machinery of the cells to multiply itself. Now you take this virus, you cut out the pieces that are dangerous so that it will still stick and be engulfed but not develop in the cell. And then you add to this some other tools that the virus then can use to cut out the bad DNA, stick in, splice in the good DNA. This is a mechanism that is used now to do gene therapy using viruses.
The ability to tamper with our genes has obvious applications. We can change DNA to prevent or cure hereditary diseases. We can alter the DNA of donor organs that are to be used for transplants so that the body of the recipient won't reject them. The organ doesn't even need to come from a human being. It could perfectly well be that of an animal.
Pigs would be a good supply of kidneys or other organs to transplant in humans. But because of the difference between the two species, the pig kidney or the pig liver will be rejected by the human. So if we can humanize the pig kidney by putting in some human DNA, which will make the cells look a little bit more human, so that they are not rejected by the person immediately, then there's a better chance that you'll have a take. And this is tried to humanize animal tissues, and it's becoming a big industry because we need more organs.
I think increasingly we're going to start realizing that this body is not sacred. The way we are is not some kind of God-given plan. It's really a pure random accident. We take two sets of genes and we shuffle them and something comes out. Sometimes it's a wonderful product, sometimes it has a hole in the heart, sometimes it has psychosis or tendencies towards extreme anger, has addictive problems, can't concentrate, all kinds of defects. To say, oh, that's normal, that's sacred, that's good, to me is rather absurd. It's random. There's not a plan there that we're thwarting. So genetic engineering seems to me one of the most moral things we can do.
A single species is defined by the isolation of our genetics, reproductive isolation. But when you begin to take genes from different species to mix together all of the genetics that is available among all animals, and also to design new alterations to the genetics, well, reproductive isolation really doesn't have much meaning anymore. And so you can imagine all sorts of forms and that will evolve in the future.
In the future, we will be able to sculpt our bodies like living sculpture. Our bodies could be beautiful electronic designs that shimmer prismatically in the light, in the morning light. It could change forms. It could become a piece of marble on one hand and then totally mutate into some fluid type of luminescent, snake-like quality. After all, the body is an extension of fashion.
You can rearrange the human body and try to make humans fly, even though humans are very heavy. And some mammals fly, like bats fly, but they're much lighter. But it's an intriguing question because it brings up the issue of not just trying to take an injured human and returning them to normal, but taking a human and making them superhuman, making them go beyond.
Our future is not to try and hold back genetic engineering, but to try and use it in a way that best serves us. If our children can be more intelligent and healthier and live longer lives through altering our genetics, why would we not want to do it? I mean, imagine if other children could live for 2 centuries, and if you could only live for 80 years because your parents believed that it was improper to tamper with human genetics. You would not be pleased with that decision. The same thing if your IQ were a normal IQ and all of your classmates were much, much brighter because there had been sort of some biological or genetic manipulation that was possible. You'd feel very angry about this.
Once we know exactly how our DNA code functions, we will be able to enhance our bodies. Human life will improve from one generation to the next as we control and accelerate natural evolution. But a rival to mankind is appearing on the horizon, a rival that is evolving much faster.
Are people becoming obsolete? A giant electronic brain has started cogitating at the University of Pennsylvania. It's made of vacuum tubes like your radio, and it can add up a column of figures a yard long in a second. It's the world's first electronic computer. Right now, it's solving mathematical problems for the U.S. Army, but who knows, someday a machine like this may check up on your income tax.
So imagine the human abilities as kind of a landscape with some peaks, which are the things we do well, and some valleys, which are the things we do really, really badly. There are things that we do extremely well, which are things that were important in our survival for most of our evolutionary history, things like moving around and socially interacting and perceiving the world. And there are things that we have only recently learned how to do, things like general reasoning. An extreme example is arithmetic, where we are very, very, very inefficient. Computers are different. They are universal machines. With an efficient program, they can do almost any one of these tasks equally well in some abstract informational sense. So the skill of computers can be likened to a water level that's uniform. The water level is rising. And it's rising at a rate that is about 10 million times faster than the rate at which we evolved those abilities. That and a number of other calculations lead me to believe that the highest peaks will be covered by this rising flood in less than 50 years. But once the level of computer competence has risen beyond the best human engineers, then there won't be any human engineers. There will be robotic or computer engineers.
We might one day duplicate man, his form, his body, his actions and reactions, carefully engineered for lifelike appearance.
Non-biological intelligence is growing exponentially. Biological intelligence isn't really growing at all. Or if it's growing at such a slow rate that it's not noticeable. Which is why non-biological intelligence ultimately will become dominant.
Yeah, right. So it's 101, 100, 010, or 001. Yeah, that's all.
Will computers ever become conscious beings? Computers calculate using zeros and ones. Therefore, many people, among them some scientists, believe that they will never become more than sophisticated calculation machines.
The great scientist, Professor Frankenstein, when his monster moved for the first time, without knowing it, he spoke of the absolute distinction between the artificial brain and the human brain when he said, "It's alive."
It's alive! It's alive! It's alive! It's alive!
In theory is not good enough. No, I believe.
So the difference between biological and artificial intelligence can be summed up in one word: life. At least that's what Dr. White believes. It is indeed hard to imagine that one day digital machines created by us will have a consciousness.
Ultimately, it literally gets confused until ultimately it falls over onto its butt. There we go.
But then, why do we think of ourselves as such unique and sacred mechanisms? After all, we are also defined by a digital code, our DNA code. The approach used today in building artificial intelligence is not to try to program conscious beings, but instead to let those robots learn by themselves, to acquire knowledge step by step, just as we do.
There's no actual programming done in these things. What we do is we create a neural topology, like the way that our nervous network is designed, the brain on top and all these little tendrils that go to all our muscles. And then what happens is that because there's no other solution for it, when this thing powers on, it learns to walk. You can actually watch it. When it comes up, it goes completely crazy. Okay? And all its legs, it basically comes up in a state of epileptic fit. And then it winds up being able to figure its way out. And as you watch, there, it just learned to walk. So it programmed itself in a very short period of time. Most people have always assumed that you're supposed to build a brain and then sort of like a body will fall out of it, right? The thing is, of course, is that well over half the species on the planet have no brain to speak of at all, but they manage to survive and move around very well and very effectively. So what we've done is we've tried to evolve things from the bottom up. And in the process, we have not yet evolved brains, but we have managed to evolve very effective nervous systems.
Self-organizing systems such as neural networks can yield remarkable results. Carl Sims made a software program of small cubic creatures that were able to evolve. Those that moved the fastest got the right to procreate. But there was always random change built into their program, into their genes, so to speak, in order to make them evolve. And Sims watched the strange creatures that appeared on his computer screen. He also let them compete for a green cube. Then, something extraordinary happened that wasn't programmed. One of the creatures jumped over the green cube and attacked its competitor before going for the cube. Evolution had produced a creature that was the most able to compete, and therefore to survive. It was just a software program, but one that organized itself. One day, very powerful computers may surprise us.
First we say that if a computer could play chess, then it would think like us. And then we get a computer to play chess and we say, that's really not thinking. And the answer is that we don't really know what thinking is. I would argue that machines do a pretty good job right now at thinking. And they don't do as good a job at creating, although we don't really know what creating is. And they don't do a very good job at having a soul, but we don't really know what a soul is. But when we can define it, they do a pretty good job at doing it.
I'm not love you. Aw, he say he loves me. I love you too.
If we give machines a body, if we build embodied entities, if we let them right from the start being part of a community, if we make them learn interacting with us, learning to distinguish between themselves and the environment, learning to, then automatically things like love and stuff like that will emerge. A baby, a newborn baby, doesn't have those values at all. It learns it by interacting with its parents, its family, and its community.
Is it love that these robots will learn once they become intelligent, or will they turn against their creators?
And historically, humans don't do well living side by side with other things that are human-like. One or the other survives and the other goes away. We don't do well in cooperation. 500 years ago, when humans entered the New World, it was not a good outcome for the natives. And I don't expect as we enter this newer world, this brave new world, that it will be pleasant for the losers. And the winners may be some transhuman thing, but the losers, or the typical inhabitants of the last 500 years, won't be treated well, because that's not been the history of man, going all the way back to what happened to the Neanderthals when the Homo sapiens arrived. They didn't live in cooperation, even though they're very similar.
My worry is that if artificial intelligence is allowed to develop entirely separately from us, and if it develops a lot more quickly than we can alter our biological bodies, then it may become vastly more intelligent, more wise than us, and we'll get left behind. And personally, I don't want to be left behind. I'd rather be up there with the most advanced creatures.
If we don't want to end up obsolete at birth, if we want to stay the most advanced beings, there seems to be only one solution: to become robots ourselves.
Whether we like it or not, we're becoming cyborgs. We're becoming transhumans. Transhuman is an evolution from human to post-human, where we're no longer exclusively biological. So the cyborg is having all sorts of add-ons. Are we walking around naked? No, we have clothes. We have eyeglasses. We have earplugs. Now these are very, very basic, early add-ons to our biology. We're also having much more innumerable add-ons, prosthetic parts, inorganic hearts. We will see much more advanced prosthetics in the years to come. Eventually we'll have entirely prosthetic bodies.
Human as a design is a wonderful design, but humans as a design have some faults. One fault is we were not designed for the modern age. The industrial age has equipment moving faster than we are, and equipment that's very large that crushes us. So we were designed with an endoskeleton, meaning our bones are on the inside, with our soft tissue on the outside. The world would be better for us now if we had our bones on the outside like an exoskeleton. So we were like a beetle.
Post-human, I think, will be post-biological. By that I mean that it'll be a gradual process. There won't be any sudden transition to a different form. I think we'll gradually integrate more and more technology into our bodies. We'll be replacing our organs with more efficient organs. We'll gradually replace this neural tissue because it dies off after a while. It's easily subjected to chemical damage. So eventually I think we'll replace our brain cells with essentially computerized parts. It'll be much more efficient, much more powerful.
To become cyborgs able to compete with the rapid evolution of computers, we first have to understand how our own brains function. The research in this area has boomed in recent years. One of the factors behind this is the development in scanning techniques. They are now at the level that enables us to observe individual nerve cells at work in living animals.
So is this dying out here? Or is that
it's in the process of growing in.
The technique is based on fluorescent jellyfish. Dr. Lichtman isolated the gene responsible for the fluorescence. He implanted it in mice and continued his experiments until he had a mouse of which only the brain cells were fluorescent.
They're genetically engineered so that these are now heritable strains of mice. We have a yellow mouse strain, we have a blue mouse strain, we have a mouse strain where only a few cells are labeled, and we're now generating mice that have multiple colors in them. We call them brainbow mice.
With this technique, we can see individual nerve cells make connections with each other and emit signals.
It's really quite jaw-dropping. It's beautiful when you look inside and see these nerve cells that have always been there, but never easy to see before in living animals.
This technique is used now by many laboratories, helping in their efforts to understand how the brain functions. Other scientists use a completely different approach. They take the brain cells apart and let them grow in a small dish on top of a computer chip. The problem with this technique is that it is extremely difficult to place each cell exactly on the right connection point. A team of researchers at IMEC has recently found the trick. They printed a pattern on the chip with a product that the brain cells love to eat. While consuming the product, the cells get stuck to the right spot and their tentacles are guided by the pattern. This way, the whole network of brain cells can be entirely controlled. Some scientists have already been experimenting with such brain dishes. Their chips were less precise, but their results sometimes remarkable.
Let me disconnect the light show.
Dr. DeMars, for instance, tries to communicate with his brain dishes and teach them several tasks.
So each of these dishes contains about 20,000 or so neurons, which are firing away as we speak. So each one's an individual network, and they'll fire spontaneously. We take living rat neurons, and they will rapidly form a neural network. And we have this grid of electrodes underneath the surface of these living neurons, and we can listen to the conversation among the neurons. And we can also stimulate activity within that network. We can send in different patterns of stimulation and look at how the network changes as a result of those stimulations. And that's how we do what we do.
What he does is to teach his brain dishes how to control an airplane.
The network can essentially fly the aircraft in a pretty optimal way. So it won't overcorrect too much, and it'll be able to stabilize it in a wide variety of conditions. I think I've programmed like a 50-knot crosswind into this one. It was what it looks like. You can see it, the aircraft, when it hits one of these crosswinds, how it begins to oscillate. The oldest dish that I've had is at 2 years. And the only reason why that dish died was because we were moving the lab from Caltech to Georgia Tech. Otherwise, that dish would probably still be alive today. Each dish has a characteristic, so you can learn to recognize one dish from another dish. They're demanding, though. You have to feed them once a week.
More and more, we will be able to measure and understand how our brain cells function. Deciphering our consciousness is another question. But the experiments of Dr. Yang Dan have proved that in principle, it is possible to read and to understand the brain.
I didn't know that we started this thing again. So this is a digitized movie. We present this to the animal, and we record the activity of their visual neurons. And these electrical signals that we recorded from will travel through these cables.
She managed to tap the vision from the brain of a cat and to reconstruct what the cat sees onto a computer screen.
So this is a digitized movie. This particular movie is a short clip from Indiana Jones, I think.
Here we see the two images next to each other. On the left, the image that was shown to the cat. At the right, the image that is tapped out of the cat's brain.
The picture has a lot of random flickering, the noise. That's probably the noise of the actual neurons, because they sometimes fire spontaneous spikes. We consider those noise, but maybe they reflect something else, maybe the thoughts or something. But we can't distinguish that. So when we use all of those, thinking that they represent visual information, this is the reconstruction that we come up with.
It is the first time an image was tapped from a brain. It proves that we can read and understand the grammar of it. The face is recognizable, but I still can't avoid the impression that the face has something cat-like. Dr. Theodore Berger is head of the Center for Neuroengineering at the University of Southern California. With a team of top scientists from different disciplines, such as neurology and computer programming, they have collaborated to develop a chip that can replace parts of the brain, or, on a longer time frame, add more brain power.
One of the first things that we do in this process is to actually study this part of the brain experimentally. We need to know very precisely how it behaves if we're going to reproduce that function in a computer chip and put it back into the brain. So what we do is to take the brains out of the animals that we use for these experiments and then slice up this brain tissue and keep the slices alive in a dish, and we study the electrical properties of these neurons. Neurons happen to use electrical impulses to communicate with each other the same way that transistors do in a circuit. And so essentially what we do is to test the cells to find out, when we give them computer-generated signals of all possible signals, we give them random signals and we ask, how do they behave? And by looking at the translation, we figure out what the function is, and we can describe that function with a set of mathematical equations.
This portion is simulate one neuron.
My colleagues have taken that mathematical model and built a microchip circuit, very small, millimeter by a millimeter. So we can take a part of the hippocampus that's a circuit, we can cut out parts of it, throw it away, and we replace it with a microchip. And so now the whole circuit works just like the biological circuit, so that incoming information looks like, incoming temporal patterns look like outgoing temporal patterns, just like it does for the biological piece of tissue. But now there's a microchip in there, instead of having biology in there.
The chip is presently being tested on animals. One problem that remains is how to connect the chip to the brain. Today's technology uses tiny electrodes, but in the future, another option might be to put some brain cells directly onto the connection points of the chip. They would then be guided to form connections at exact points within the brain in order to establish the perfect interface.
Ça pourra permettre de réparer des cerveaux endommagés à la suite d'accidents, de blessures, n'importe quoi, de maladies. Mais d'un autre côté, ça permettra aussi de faire une communication peut-être directe de cerveau à cerveau. Des choses qui sont effectivement pour l'instant limitées, la communication intra-humaine étant limitée avec la parole, alors que là, l'idée qu'on peut directement peut-être communiquer des expériences globales de cerveau à cerveau, c'est quand même quelque chose de fabuleux qu'on peut rêver. Et puis bon, il y a des tas d'autres applications peut-être plus pratiques à court terme.
One such concrete application has already been realized. The chip is used to recognize sounds since it can literally do that with the same accuracy as we do.
So we've used these brain-based models as to develop acoustic recognizers. So we train them in the same way that your brain learns to recognize a particular sound. And one of the first sounds that we've developed is one for gunshot recognition. It's a model of how hippocampal neurons communicate with one another. That's all it is, biology.
You got one over there across the park, then they have another one they used to have right there. Then they just put up another one over here 2 days ago. These high-tech cameras, they are called Crime Stoppers. If a gunshot goes off to my left or to my right, the camera automatically traces down the sound of the gunfire and zooms in and takes pictures.
You cannot buy a system today that can recognize speech signals or any other signal in noisy environments. They don't work. But your brain works that way, and because our model is based on the brain, our models work in noisy environments.
And the thing is, there are no cameras installed in the white neighborhood, but we have 5, 6 cameras in the black neighborhood. So the black neighborhood is being watched.
If an airline pilot is about to press the wrong button, it may be important enough to think about trying to identify what the patterns of thought are, what the memory patterns are, and if the person is recalling pressing the button so that we eject right, when they're not supposed to, or press the button so that a bomb goes off and they're not supposed to, then you might want to intervene and prevent that. I'm part of another project that is funded by DARPA that's trying to understand exactly that. I mean, how is information represented in the brain?
And science is supposed to have all the answers. But this has got to work.
It's not going to fail, not after we've come this far. We have here, for all practical purposes, a normal human being, except for his electronic sensory control system, of course.
On devrait, avec des localisations donc de ces circuits électroniques dans différents endroits du cerveau, de pouvoir lire le contenu du cerveau et le mettre sur un disque dur, le transmettre directement sur à une autre personne, etc., etc.
Part of our problem is in getting enough sensors into the brain without destroying it, getting enough sensors in there so that we can extract enough information to infer what the total pattern of activity is. And if we can do that, then we have to develop a mathematical model of how information along all those pathways develops and is processed. And so for the next few years, that's going to be the task. Now, if we can do that, then we'll get to the finish line. We will get to the finish line.
It's a conservative statement to say that by 2025, we'll be able to look inside your brain, see everything that's going on, all the interneuronal connections, all the synaptic clefts, all the neurotransmitter strengths, and create a huge database and copy down every salient detail, and then reinstantiate that information in a neural computer of sufficient capacity and create basically a copy of the thinking process that takes place in your brain. Now that's one scenario, but it's really an existence proof to show that we can tap the secrets of intelligence that exist in, let's say, the human brain. Once we've scanned that information, we can also understand it, see how it's organized, improve on it. We can extend it. We can make the memory 1,000 times bigger. We can make it faster. We can expand the perceptual capabilities.
To transfer your mind to a computer, this seems to be the ultimate dream of many scientists. To liberate us from our old body that is becoming obsolete in this technological world. We would then go on living as free spirits in cyberspace.
I'm not interested in a future where there are post-human beings if I'm not one of them. I want to be there. It's very important to me that I live and thrive in the future, not just to think about some robots taking off into space. I want to be there.
So in a way, mind uploading is a shortcut around artificial intelligence that will allow us to have machines with human minds.
I'm hoping that we could fit on a CD-ROM. That's 600 megabytes. And I'll bet that that's all you need to copy a person.
So it's a difficult time to predict what these new humans will be like. I think it's important to include the third component, which is the virtual, along with the artificial and along with the flesh. But how that mixture goes together in a cooperative versus a competitive way is hard to predict. It's very interesting. It's a great time to live in. But I'm anxious to wait 50 years to see what the answer is.
Reality and virtual reality are beginning to merge. To understand how this will occur, we have to look at one more technology slated to overshadow all other branches of technology. It's nanotechnology, the means of getting control over matter, atom by atom.
So what we're going to do is move this atom from this location here to a location right over here. We'll move it just along this path here. Now you got to get excited about that. You just got to get excited about that.
Scientists are now able to grab one single atom and move it to another place. It's a small step for an atom, but a giant leap for mankind. If we start making things by building them atom by atom, we can make almost anything we want.
Manufactured products are made from atoms, and the properties of those products depend on how the atoms are arranged. Now, today's manufacturing technologies arrange atoms very crudely and statistically, but in the future, with nanotechnology, we'll be able to arrange the fundamental building blocks of matter in precisely the patterns we want, very flexibly and very inexpensively.
Nanotechnology will open vast opportunities for all other technologies, in particular for computing. When computer connections can be made by single atoms, computer power will increase enormously.
Computers incredibly powerful that just would let us put into a single sugar cube a computer that was more powerful than all the computers in the world combined today.
But there are many other fields in which nanotechnology will be applied. While at the end of the last millennium, most scientists believed that nanotechnology would remain science fiction, we now see its first applications already appearing on the market.
So we now make materials which purify water, which generate electricity, which generate chemical energy. And our long-term research project is to build a system that processes information, kind of like an artificial neuron. You're going to start seeing systems and processes like that proliferate within the next 45 years, in which you're going to be amazed constantly.
This rotating dot here is the first real nano engine ever made, only a few atoms in size.
I took the F1 ATPase and I stuck a little propeller on the top of it and made it spin around from one molecule. Well, now I can take many thousands of these in complex systems like we have in our bodies and make them do more sophisticated things.
The ultimate goal is to create robots as small as viruses, called nanobots. These nanobots will be more intelligent than today's computers. One possible set of applications is medical. Nanobots could be injected into the bloodstream as a kind of cleansing team to kill cancer cells, for example, or to carry out other kinds of maintenance work in the body, or even to modify the DNA code. It might seem that this is a very expensive technology, but in fact, the opposite is true. We will be able to program nanobots to reproduce themselves, just as all natural creatures do. They will then be able to grab material from their environment and use it for making copies of themselves.
Well, the basic goal of nanotechnology is to build what's called an assembler. And this is simply a very small device that can make copies of itself. And it's a programmable device, so it can be programmed to build a wide range of useful things.
Autoassemblers can be seen as a new form of life, comparable to viruses or yeast cells. They can reproduce themselves and at the same time transform matter, just as yeast cells change sugar into alcohol. The only difference is that these new creatures can be programmed to carry out whatever task we want them to. Change carbon into diamonds, perhaps, or create food.
Molecular nanotechnology is to physical reality what computer programming is to virtual reality. I think that's a bit of an exaggeration, but gives the idea. Whereas computer programmers can program software to do what they want, molecular nanotechnology will allow us to change matter at the most fundamental level. It will allow us to build just about any kind of structure to our exact specifications by moving individual atoms.
This sounds like a world of magic, where all that we imagine becomes reality. But the role of the good fairy is taken over by robots so minuscule that we cannot see them. And instead of saying the magic word, we program them to grant all our wishes. The other side of this fairy tale, however, is what is called the gray goo syndrome. Imagine that some nanobots are programmed for a terrorist action, or would simply tilt and start reproducing themselves endlessly. In a rapid chain reaction, the Earth would be reduced within 72 hours into a gray goo of swarming nanobots. Most scientists, however, stress that such a scenario is very unlikely. We will have nanotechnology to control nanotechnology, and it will also provide the ultimate escape route. We will be able to inject a certain number of nanobots into our bodies, where they will locate our brain cells and copy their functioning. With no effort, we will get a hardware copy of our consciousness that will then send a software copy to a computer, where more copies can be made, or where our consciousness will be allowed to merge with other souls and software programs. Then we will be ready to leave this planet and start the exploration of the universe. What is our place in this magical world where everything can be transformed? How will people deal with such a future? Or is it something that by definition goes beyond our human capacities to understand? Something that only transhumans will be able to grasp? Will we stay as we are and watch with wonder from the sidelines? Or will we upload ourselves and participate in the world as super beings? Let yourself upload to a network of nanocomputers and let the wind carry you.
It's important to recognize that the post-human epoch is coming. It really is. It's what we want, and it's kind of, you can see it written in the pages of magazines. the word of the prophet is on the subway walls here. We really, really do want to violate human limits now, and we're getting closer and closer to the ability to do it. But it's also important to realize that this is not the end of history. It doesn't solve any of our other problems. It just creates new problems that are going to intensify. And there's going to be more than one kind of post-humanity. And the mere fact that you're no longer human doesn't mean you don't have the same personality problems that you did before. It doesn't liberate you from yourself. It probably makes you more than you were before, not less. You're not going to clank and beep like RoboCop. You're just going to have new abilities and new powers, and dealing with power is troublesome. If you have more power, you have more responsibility, not less.